Hello and welcome to Algebra 2. Today we are discussing Chapter 10.5, which covers hyperbolas. So we're going to start out with the definition of a hyperbola, and it is the set of all points P such that the difference of the distance from P to the two fixed points called the foci is a constant. Now, this is very similar to definition of an ellipse, except for an ellipse it was the sum, and so this is the difference. So we still have two fixed points called focal points, and so a hyperbola actually goes like this. Okay, similar to the rational equations that we graphed in the fact that it has two branches. And so if we pick any point on our hyperbola, that the difference of those distances is a constant. So the difference of, we can call it d1, d2, is going to equal the same number as the distance of, let's do d3 minus d4, and I made them kind of look the same there, but it would be the same number as from there to there. And so any point at all on a hyperbola, the difference between those distances is a constant. So we have some parts to a hyperbola, and first we still have vertices. So I kind of already drew in what it looked like, so let's start with that again. So we're going to have two branches, and they're either going to go left, right, or up, down. So we'll just start with the left, right. So there's my two branches. And so our vertices are the points where the line through the foci intersects the hyperbola. So the foci are actually out past. So similar to where your focal point would be for a parabola. Okay, and so if we connect those, where it crosses the hyperbola, those are our vertices. So there's my vertices. The transverse axis is this segment joining the vertices. So the distance just from those two vertices is my transverse axis. So we'll say that was green. We still have a center, and it's the midpoint of the transverse axis. And we have our two branches. And we also have two asymptotes. And how we get those asymptotes is we do the diagonals of a rectangle that contains the hyperbola's center. So how we get this rectangle is there's still some points out here, and the book doesn't call them co-vertices, but they're going to be very similar to our co-vertices we talked about. And if I drew in a rectangle that contained the vertices and co-vertices, and then if I drew in the diagonals of that rectangle, those would be the asymptotes of my hyperbola. So if we have this rectangle, then we can have these asymptotes. We know where our hyperbola is headed. So here's probably a better picture. So we have left, right, up, down. And notice the A, B's, and C's still. Focus is still C, vertex is still A, and then we have this co-vertex that is B. And our equation, so we have different equations for whether it opens up, down, left, or right. Notice they look very similar to the equation for the ellipse, except it's a minus in the middle. Okay, minus in the middle still equals 1. All right, make sure you got that stuff written down, and let's look at some more equations here real quick. So the difference here, and I should have pointed on this last slide, but notice A squared is under the first term, B squared is under the second term. So we're in an ellipse where the A and the B switch places. The A and the B don't switch places here. It's the X and the Y that switch places. So if the X is first, you're talking about a horizontal, so we're opening left or right. If the Y is first, we're opening vertically or up and down. Okay. Asymptotes, because we want to go both ways for those lines, plus or minus. And notice the slope is b over a or a over b. We get that from our a and our b. And our vertices, plus or minus a. And again, we have a relationship between C and A and B, C being the distance to those foci. This time, though, it's C squared equals A squared plus B squared. All right, so if you have all that written down, let's start using it. Okay, so looking at this equation, the first thing we're going to notice is it's supposed to be equal to 1. And so to remedy that, we're going to divide by 144. We're going to divide everything by 144. Okay. And looking at this fraction here, 9 over 144 is 1/16. So I could write that as x squared over 16 minus 16 over 144 happens to be 1/9. So that becomes y squared over 9 equals 1. So first of all, we got to put it in the right form. So x is first, so that is going to mean horizontal. Right, left and right. And we know these are centered at 0, 0. So I'm going to go ahead. So I know this is the center. I know my A is 4, B is 3, because that's A squared. A squared is 16, B squared is 9. So my A goes out to my vertices. So I'm going to go 4, there's a vertex, there's a vertex. I'm going to go up and down 3. There then is my rectangle. And my asymptotes are going to extend as the diagonals of this rectangle. And if you wanted to be really specific, you wrote down that the asymptotes have equations of y equals plus or minus b over a to the x, which would be plus or minus 3/4 x. So from 0, 0, you could go up 3 and over 4, that would put you there, up 3 and over 4. And you could count all of your asymptotes and make sure you're at exactly the right place. And then what we're going to do, though, to draw this in, we're going to kind of take the shortcut here on these, is I know it has to stay inside of these asymptotes, and I know where the vertex is. There's your hyperbola. So the next thing we want to do is we want to write an equation, and it gives us a focal point. Actually gives us 2 focal points and 2 vertices. So the distance to those focal points is your C value. So that's this tells me that C is 5, and this tells me, either one of these here, that A is 3, and I really got to figure out, is this opening left, right, or up, down? Well, looking at where these points are, if they all have zeros for the x's, these are all on the y-axis. So if they're on the y-axis, and I'm talking my vertices are on the y-axis, this opens up, down. In which case, y squared is first. Okay, so if all my points are on the y-axis, it has to open up and down. Alright, so we have y squared over, well, we already figured out a, so a squared would be 9. We have not yet figured out b. But if we use our equation, c squared equals a squared plus b squared, for hyperbola we got a plus in there, and thus b squared equals c squared minus a squared. So c squared is 25 minus 9, which is 16, and that's b squared, and we're going to leave it just like that. There is the equation of our hyperbola. Alright, a real-life example here. We have a hyperbolic mirror, has a cross-section represented by y squared over 9 minus x squared over 25 equals 1. How far is the mirror from the lens? Well, let me explain a little bit here. The lens of what? What are we talking about? If you have a hyperbolic mirror, and so really, if we're looking, here's my hyperbola here, and we have two focal points, okay, because each one is going to have a focal point. And you put a camera at one of the focal points. And so really we'd end up not using both hyperbolas. So let's say we put the camera here. You're going to point it towards the other part. And what you actually get is you get a 360-degree picture because you have every angle coming in to this mirror here, and it's all going to bounce down to that other focal point, that camera. Okay, so the question is, how far is the mirror from the lens? Meaning, what is this distance? Okay, well at the moment we're still centered at 0, 0. And I know from my equation that A is 3 and B is 5. So I know to my vertex, from the center to my vertex, I know that is 3. Okay, and I know this one up here would be 3. So then, we try to pick a color here that we haven't used. What is either the rest of this distance, or can I go like all the way to the center? What's this distance? Well, if this is a focal point, that distance is C. So if I could find C, I could add 3 to it and get my total distance from this mirror. Well, so if we use our equation, c squared equals a squared plus b squared, and thus we know a squared is 9 and b squared is 25. C squared is 34. Square root both sides, so c is the square root of 34. So I know this much is the square root of 34, and I'm going to add 3 more. So the distance from the mirror to the lens is going to be 3 plus the square root of 34. And if you wanted to change that into a decimal, it is roughly 8.83 inches. So just really utilizing our A, B, and C and what they represent and finding that distance there. Okay, one last word problem we're going to look at. Here we have the diagram that shows the hyperbolic cross-sectional area of an hourglass. So if you took an hourglass and you cut a little sliver out of it going up and down, we get a shape like this. And the first thing it wants us to do is write an equation. So upon inspecting this, I believe it's going to be a hyperbola that opens to the left and the right. So my base equation I'm going to use then starts with x squared. If it opens left or right, x squared comes first. And so what I'm missing then is a and b. Okay, well, let's see here. A goes from the center to the vertex, and that has to be the vertex. So a would be 2. So we got A. A is 2. But B goes from the center to that co-vertex, not really called the co-vertex, but we're calling it the co-vertex. It's this rectangle, but I don't know where the rectangle is. I mean, I know these two sides, but is the rectangle here? Is the rectangle here? Is the rectangle there? I don't know where this rectangle is. So I really can't use my picture to directly solve for B like I could A. So if I, though, have an equation that has an x and a y, and I have a and I have one unknown term, what I could do is I could pick any point on my parabola, you don't want to pick a point, you don't want to pick 2, 0, you don't want to pick something with a y that's 0 because it's going to make my b 0 out. But any other point except one with a y is 0 would work, and I could plug in my values. So if this is x and this is y, so I'm going to get 4 squared over 2 squared, because I know what a is, minus 6 squared over b squared equals 1. Could we use this and solve for b? I'll see where I'm going, right? If you have everything except one term, you can solve for it. So 16 over 4 minus 36 over b squared equals 1. So this is going to be 4 minus 36 over b squared equals 1. Subtract 4 from both sides. Negative 36 over b squared equals negative 3. I'm going to go ahead and multiply each side by negative 1. So 36 over b squared equals 3. Cross multiply. 3b squared equals 36. b squared equals 12. And I can stop there because really I need b squared and not b. So my equation then is x squared over 4, because that's my a squared, minus y squared over 12 equals 1. So there's my equation. And then at the height of 7 inches, how wide is the hourglass? Well, what this is asking me for, let me pick a different color here, is at a height of 7. So meaning height of 7 inches, we got to start at the bottom, and this is actually the bottom of the hourglass. So at a height of 7 inches, we're going to go up 2, 4, 6. 7 puts us at y equals 1. Okay, so then the question is, what's the distance between that point and that point? Well, let me find my x there. So if I know y is 1, I can come and I can make y be 1, and I know 1 squared is still 1. So we get x squared over 4 equals 1 and a 12th. Okay, so I added a 12th to both sides. Multiply by 4, x squared equals, ends up being 4 and a 3rd. And then I want to square root both sides. So x is plus or minus 2.08. So meaning my 2 points are 2.081 and negative 2.081. And what's the distance between those? Well, really it's just 2.08 times 2, because it's 2.08 out either side. So the distance ends up being 4.16 inches. So just specifically finding the points we want and then finding that distance between them. Alright, that's what I have for 10.5. Hopefully it answered your questions. If not, come see me, and if I don't see you before then, I will see you in class next time. Have a great day.